this is the contents I'm going to talk about today. So first of all, maybe it's since it is a summer school, I think it's good to start with the basic stuff. So I'm going to introduce about the random variable theory very briefly, and then number indicator physics briefly, and about the what kind of theoretical approaches to the number indicator physics. And then next, I'm going to talk about my research work with motivation and theoretical model and results. So let me start with the introduction. Oh yeah. So in random variable theory, the most important concept is a quasi-particle. So here, to understand the quasi-particle concept, let me just start from the very basic thoughts without any abstraction. So this is a quasi-Fermi gas model. Then for this model, actually, you can calculate the spectral function exactly. So here I put approximate, but it is exact. Yeah. Then it is given by this kind of delta function. And so this is exact relation. However, in the presence of interaction, then becomes very liquid. So, but still, I mean, surprisingly, it has a similar structure to the Fermi gas model. So it still have a delta-like peak. So this is the reason why people call it as a quasi-particle. And this is a theoretical formulation, but intuitively there is a way to understand it more. Yeah. So, so suppose there, I mean, for very tough model, let's suppose particle, I mean, let's consider particles as an IN state with definite momentum. from microscopic details. So yeah, maybe it's a universal. So then, how can you understand? I mean, why it is so universal in nature? I mean, why it is so? There's a one way to understand this universal thing, which is nothing but RG. So we can understand this universal thing from one equation. So starting from the following microscopic Hamiltonian or action. The first term is a kinetic action, and the second term is a short range interaction term. And this is due to, I mean, actually we need to consider Coulomb interaction, which is a long range interaction, right? But due to large Fermi surface, there is actually a screening happens, which is called Thomas Fermi screening. So we can start from this kind of short range interaction. Then under RG, I mean, if you go to low energy states, then you can obtain following effective action. And here, since, I mean, due to the Landau momentum conservation law and the Fermi surface shape, actually there's not many, only 4 scattering remains, which means, I mean, here K1, K2, K3, K4 can be any arbitrary number, and which satisfy the momentum conservation. So here K1 plus K3 should be same as K2 plus K4. But due to this, I mean, Fermi surface geometry, we can actually obtain, observe that K1 is almost same as K2, and K3 is almost same as K4. So which we call, usually we call it forward scattering. So in this case, then as you know, I mean, since K1 and K2 are very similar, right? So we can just approximate with K. Then psi and psi can be written as an NK, which is a equation number. Then from this action, actually you can obtain following energy function, which is nothing but Landau function. So from this microscopic action, we can actually derive Landau's function. Yeah. So it is very remarkable result because Landau only formulate this function based on this intuition about such particles. So from this we can say that Landau Fermi liquid is a higher fixed point of a fermion field theory with short range. Then, however, so this is about up to now it was about Fermi liquid. However, there are several materials which do not show this kind of metallic states, and the most famous example is superconduction. And here, this is a phase transition phase diagram of 2 points. And this is a quantum critical point. And the left part is a Stochastic phase. The right part is a Fermi liquid. And then between them, there appears some metallic states, which people usually call strange metal. So it does not satisfy the usual Fermi liquid behavior. And so the most maybe popular property of this strange metallic state is this resistivity is proportional to T linearly, not T squared. So which is different from the Landau Fermi liquid theory. So starting from this material, and not only this material, but also ion-based conductor or maybe heavier materials, these states are observed universally. So this is new metallic states which cannot be described by usual Landau Fermi distribution. So this is experimental observation, and to understand this non-Fermic for people, so that's why people call it non-Fermic states. So to understand this non-Fermic states, we can consider following simple model. I'm going to show you this model first. So this is a phase diagram, a schematic phase diagram. Here the left part is the ordered states, and the right part is non-ordered states, and between them, non-Fermi states appear. So And we can actually describe this phase transition, quantum phase transition, using following people interaction. So using random interval. Here, P is your boson parameter. And yeah, so yeah, as I already told you, there's a two states, and at the quantum critical points, this has a mathless boson particle. And this mathless boson particle, if this mathless boson particle occurs to the fermions, then if you give the long range interaction, and then this give non-parametric space. So this is a comparison between lambda parametric space and non-parametric space. The first one is start from the short transition. But in case of non-parametric space, since it is nearby, it occurs to the massless bosonic states, and this massless bosonic states mediate the interaction between fermion long-range interaction. So this is a key difference. And also, there is no quantum particle in non-parametric states, so which exists in parametric states. Then how can you understand it? So here, this is a bosonic particle, which massless bosonic particle, and this massless bosonic particle occurs to the Fermi surface or Fermi fields, and these Fermi fields, due to so you can consider some bosonic particle propagates, and it feels some particle excitation, and due to this particle excitation, then in terms of diagram, they obtain this kind of lambda damping effect. So it is called damping because bosonic particles propagate, but there are some particle excitation happening. So it loses energy for maybe coherence. So that's why we call it damping. And this lambda damped bosonic particle again, interact with Fermi fields through this kind of two-loop diagram. So then from this two-loop diagram, we can obtain following very weird form of self-energy. And actually, this self-energy is dominant in the low energy compared to this I omega, right? Because it has a lower power. So in the low energy of in the small omega, you can see this term become larger compared to this term. So this is a key difference compared to the parametric theory. In parametric theory, this term is given by omega square usually. So in the low energy, you can ignore this second self-energy term and you can only keep this I omega. But in this case, in non-parametric space, this self-energy dominates over low energy space. And from this self-energy, actually, we can obtain the wave function qualification constant, and we can see in the low energy limit it goes to 0. So which means we cannot consider them as a particle case which have a finite z. So there is no particle in the non-parametric space. And so so Fermi surface with methylic boson, which then it results in particle dissipation. And so what is our minimum result for non-parametric space? So up to now we have think about some property of non-parametric space. So this is actually minimum result of non-parametric space. So the first term is a just kinetic term. The second term is a boson kinetic term of bosonic order parameter and interaction term among these bosonic order parameter. And the final term is a equal-like term, which couples the bosonic order parameter and fermions. And depending on the system, so here we can consider also the momentum vector of D, the bosonic order parameter. So if this order parameter does not have due periodicity, then it corresponds to Q equals 0 case. And since Q equals 0, we can consider this boson order parameter gives the momentum to these fermion fields. So in this case, since Q equals 0, so all Fermi surface become hot or non-Fermi states. However, there is another case, which I will concentrate later. So this is case when charge density weight or spin density are considered. So in this case, there is, in case of spin density wave, it forms antiferromagnetic order. Then Q is given by some finite value depending on periodicity, and it turns out that only the Fermi surface which are connected by this Q or the Q nesting vector are strongly coupled to the boson electrons. So this is called this is a Q equal non-zero case. So now starting from this very looking very simple Lagrangian, the question is that can we find the higher fixed point, which describe the universal of a non-Fermi state like lambda Fermi states. So it is actually a question many condensed matter theorists try to answer. And now I'm going to review some famous approaches and which fails eventually. So first of all, let me start with Harris-Mills theory. So this is the function I show you, the Lagrangian I show you. And Harris-Mills theory actually basically they try to derive a Landau-Ginzburg function for this action. So they integrate out all Fermi fields. Then actually we can derive this kind of effective action which only contains the bosonic order parameter. So then we can use some Landau-Ginzburg arguments to describe this function physical properties. So then if we do the scaling analysis, then actually it comes out that here I only express the UP photon, right? But there can be another higher order term. But it turns out that from this scaling, this all higher order term irrelevant. So which means here I show you irrelevant. So then maybe from these results, can you think? Maybe this very simple form of Landau-Ginzburg function can describe the non-Fermi space. However, in this paper, they show that this P photon or maybe higher order vortices has this kind of non-local. This does not. So it is not just given by constant value. So from this, so in the denominator, you can see there is a Q comes in. So due to this non-local term, if we do scaling analysis again, then you can see all higher order, the interaction term are marginal at equal to. So which means we cannot actually solve using this method, but we should include all possible, all higher order interaction. Right. So this is one problem. When we apply the Harris-Mills theory, and another approach. So actually from this we can get following. So integrating out the many gamma fermion is dangerous. So then people now try to understand this action without integrating fermion fields. Then starting from this one, actually we can do the scaling analysis. And based on this, the kinetic term of fermion and boson, we can do the scaling analysis. And then also this coupling constant is a relevant coupling. And so then since it is a relevant coupling, so to tame this, it becomes large and large in the low end. So to control this large quantum fluctuation, given originated from this interaction term, people introduced the n fermion physics. So this is so here you can consider n as a kind of Haba in the classical. In the from quantum mechanics to the classical theory, if we consider Haba goes to 0, then actually you can see there is a correspondence between them. And here, if we set n goes to 0, then this large, quantum fluctuation killed by this large n. So people consider maybe we can kill this kind of one-word correction using this n. So this was so then we can actually use this kind of self-consistent equation to obtain Liouville physics. So here, this is for Elias theory. However, around 20 years ago, maybe around 10 years ago, it is also shown that this Largen approach is breakdown. And so here I'm going to explain how this Largen approach is breaking down. So this is this function, right? The result interaction. And if we consider following certain stuff, with structure term effects, then we can obtain following effects. And usually people consider 6 stage n here. So then it looks like we can ignore this. Because if this n goes to very large values and compared to other values, then you can ignore this. However, it turns out that there is some output. So I'm going to show it here. So now we can obtain, by setting this term equal to this term, we can actually get a crossover energy. So which means, depending on the energy, so if the omega is larger than E mu, then the first term is larger. So we can ignore this term. But if the omega is smaller than E mu, then actually the third term becomes larger, and we cannot ignore this term. Instead, we can ignore this term, right? So, this is and actually we are interested in the low energy states. So we should consider omega is smaller than alpha. So this is a low energy region, and if we naively just set n goes to infinity, then actually we cannot see this phase, right? If the n goes to infinity, then this goes to 0, then actually we cannot see this hidden energy region. That's not perfect. So, now suppose we just ignore the first term, so this term. Let's ignore this term. Then we can have the third term become this is third term. And since n is in the denominator, since it is in the denominator, actually this order of n is increased. Due to this n in the denominator, and so we cannot ignore this kind of vertex correction term, even in the large n fraction. So which means large n method. So this is basically proved around 2009 and 2010, and actually people try to develop new analytical techniques to deal with this kind of strong fluctuation. So let's now summarize first. So in the fermionic theory, this is just conventional metallic states. And in non-fermionic states, which is metals in near the quantum critical region. So, and characteristic, So in case of the fermionic states, it has fermions with Fermi surface, and it has a short range interaction due to the Thomas Fermi screening, and it has a quasi-particle constant. It can be described by quasi-particle. However, in case of non-fermionic states, there is a massive boson which couples to these fermions, so which mediates some long-range interaction between them, and so it cannot be described by quasi-particle. So, and so this is a universal theory, a non-fermionic theory, you know. And then this is a micro theory here. I put here. But in case of non-fermionic states, we don't know the universal theory yet. So people have tried maybe Harris-Willis theory or larger technique, but it does not. It fails to derive the universal. So this is up to around 2010. So after that, many people tried to develop new techniques to derive a universal theory for these non-fermionic states. So up to here, is there any question about the non-fermionic states or fermionic theory? Then maybe I can go that. So, and recently people, there are two maybe large directions. The first one is a numerical direction. So people have developed a sign-free, quantum preemption method to deal with these quantum critical metallic states. So there are many papers, are published about this. And analytically, there is also another methods have been proposed, to control the quantum fluctuation effect. So these are, there are a lot of papers, but I just put three here. But so people have been focused on, tame the quantum fluctuation effect coming from the strong interaction. And so there are many progress, and I'm not going to review all of that, but most of researchers actually have focused on the clean case. So now I'm going to maybe give a motivation for my research. So in the real system, actually, if we consider following materials, the first one is electron doped grade and ion batch. Second one is ion batch conductor. And third one is a half fermion semiconductor. So, and all, quantum critical points are fine-tuned by the doping. So, which means, so if we do the experiment and when you do the doping, it's not easy to control this how doping regularly. So, and it means that there's always disorder effects, right? And another motivation is that in the clean system, people have also investigated about the superconducting effect in non-fermionic states, and this is a user phase diagram. So this is a superconducting dome, and in the above the superconducting dome, there is a non-fermionic state up here. However, from the studies about the clean system, people found that it showed different phase diagram. Which means here this is a superconducting dome, and this superconducting dome is much higher than the where non-fermionic states appear. So this is a problem I found, and so I'm trying to understand why it happens in clean system. So and people, I think a long time ago, there was a paper about effect of disorder in E-wave conductivity. So they found this DWF photography is suppressed by disorder effects. So I want to study this effect of disorder in equal footing with the interaction. So it was my main motivation to start this research. So let me now start with the theoretical model. So this is our physical system I was planning to study. So this is an electron dot system, and here is a hole dot, and this is electron dot. And if we see only here, then we can get following schematic phase diagram. So in the ordered phase, it shows the antiferromagnetic order, and in the non-ordered phase, it shows the lambda ferromagnetic phase. And between them, there appears a non-ferromagnetic phase. So then, as actually already introduced, there's a famous model called Haspa model. So here Haspa means that the fermion fields only at this hotspot very strongly coupled to the bosonic field. So to describe the non-ferromagnetic states, we only need to consider this hotspot. So we can obtain following. We can write down following actions. The first term is nothing but just kinetic term of fermion fields at hotspot. And the second term is a kinetic term of spin density wave of parameter. And the third term is interaction between this electron and spin density wave, so which is given by Euclid-like form. And the final term is a self-interaction, bosonic self-interaction between spin density wave and parameter. So these are the actions people have studied intensively. And in this model, I'm going to introduce the effect of disorder. So as an effect of disorder, we can consider, we consider only non-magnetic disorder effects. The first one is a random charge potential, so which couples with a fermionic fields. And another one is a random boson mass effect. So this one is, depending on the position, maybe the sign of mass can be different, right? So maybe there can be some position where, this order parameter ordered, but another position it is not. So this is a effect of random boson mass. So we consider these two effects. And so this is a clean system case. But if we consider disorder effect, then there's additional term comes in. So here, third means another Fermi surface region, except for this hotspot. So we usually call it third region, third spot. And due to this random charge potential, there can be some maybe potential this disorder scattering effect between hotspot and cold spot, and cold spot between cold spot and also random boson mass. However, it becomes very difficult problem because of presence of this cold spot. So for simplicity and because we are not interested in the transport phenomena here, so we only focus on the effect of disorder on the hotspot. So we plan to only focus on the effect of disorder on the hotspot. So we ignore the effect from the first. Then our minimal model is given like this. So the first two terms is just clean case models, and this is up to three terms. This is a clean case model, and this fourth term is the disorder scattering term between hotspots, and then final term is a random boson mass. Then to describe this disorder effects, there is a famous method called replica trick. So we can use replica trick to and we can get following there's a four fields, and also here 4 fields. So this kind of disorder average action. And then And we can also, and then due to random charge potential, there can be many scattering channels among the hotspots. So we can actually classify this kind of scattering channel based on this scattering angle. So, for example, if we only consider normal process, I mean here normal means there is no momentum. So momentum is exactly conserved. So in this case, maybe this is going to two electrons go to the same 2+ hotspot, and out is the same hotspot. And so we call it gamma 0. And if there is an angle, I mean theta 1, then we can call it theta 1t. And if they exchange, then we call it exchange theta 1. So based on using this kind of method, we can classify all hotspot scattering channel. Here delta is related to 0, I mean the total momentum is 0. And for influx case, we can also do the same thing. And since I mean these two hotspots are connected by psi nesting vector, if we multiply with 2, then it corresponds to large K. So then we can do the same thing, and we can obtain following result. So then here, so to study effect of a disorder in the low energy states, we first need to regularize the action. So there's one method proposed by Lee and Sun. And so here, this is a Fermi surface, and in K1, K2. And let's suppose we, I mean, artificially we include another dimension here, and then we wire the maintaining the this dispersion is same, or Fermi surface still remaining in 2D dimensions. Then due to then we can actually reduce the density of states, which means we can reduce the quantum fluctuation. So another and this method is I mean we use this method to reduce the quantum fluctuation effect coming from the Yukawa effect. And another one we also introduce is random Boson for random Boson mass effects. So then using this regularization method, actually then we can make interactions are marginal. So this is interaction of with disorder effects. So then there are here we can find here d equals 3 and alpha equals 1. And all this is all interaction effects are given like this. So here, if you see that this is from the random charge potential effect, it seems that it is irrelevant. However, I mean this is due to and it turns out that it is not a true expanded parameter, and actually we should find the size of a hotspot. So if it is a size of hotspot, then it becomes the massless marginal. So now we can set all interaction into marginal. So using this regularization effect, and we can obtain one loop features. So then this is when we do not consider the random charging. So here only random Boson mass effect are considered. So here this axis is gamma d, which is a random charge effect, and this axis is related to random Boson mass effect, and this axis is related to Yukawa interaction. So in the clean case, there is one clean non-Fermi case fixed point. And if in the presence of a random bosonic mass term, we can also find there is a stable fixed point, which I call random mass disordered non-Fermi case fixed point. However, unfortunately, in the presence of random charge effect, it shows the following runaway flow. So it does not go to some fix in the one loop. So, and among the random charge effects, I have shown there are many scattering channels, and among them, umflop channels become small. they die in the low energies, and the most dominant one is a direct channel, which corresponds to this red color. So in the low energies, this channel becomes most dominant. So this is a result I got from the calculation. And so in this case, this is a direct and exchange channel become very large. So lambda charge effect, but top channels become small, and you call interaction become large, but one effect, and then the Boson mass effect goes to 0. So and also dimensionless people interaction can also. So then now we can also study the effects of disorder on the superconducting channels. So here we only consider four superconducting channels, and one of them is a zero-moment G-wave superconducting channel. And we found, although since we could not find the fixed point, so we cannot obtain a universal gamma value, but if we draw a flow of gamma and then compare with clean case, so if gamma is large, means the superconducting instability is large. However, in disorder case, we can see it is suppressed by this disorder effect. So from our result, maybe it's part give some hints to understand why even if why the disorder is important. So and then if we also include the two-loop, not two-loop effect, but we also consider some partial two-loop effects to the P4 interaction and random Boson mass effects. And we found, this blue region corresponds to the one-loop effect. So here, this random charge potential become dominant. However, in the red region, if we consider two-loop effect, then we found there is a region where dominated by the random mass effects. So, and we are not very sure, but it can be maybe random singular-like phase. So this is a so this is a summary of my talk. So we consider Husband model with a possible random charge scattering channel, and in one case, we found a stable fixed point in the presence of random mass effect. However, for general case, there is no stable fixed point in one case. And within one result, it seems that the rate on the TFT is suppressed by the disorder effects. And according to our partial two-loop results, there is some possibility of random Boson mass dominate phase space. So this is a summary. And finally, I have remarks. So recently, people use this SYK model to consider this kind of disorder effects with the interaction effect equal 40. So using this kind of S1, people have considered some SYK-like model. So they, and in this case, they can solve the Green's function exactly in the Largen model, Largen case. So they have obtained various interesting results. This is another approach we can do. But in this case, there is also, artificial end comes in, and it is not easy to connect to the real material, I think. So maybe it is necessary to study the real material-based disorder effects. So this is the end of my talk, and thank you for listening.
behind the schedule, so maybe usual practice. Anyone from the audience, students, postdocs? Yes.
Can you quickly tell me what is the motivation to study the method? As for I think, if we include the latent charge group, then actually the normalization group system include the boson mass, random boson mass can be generated by one of two effects. So, in principle, we should include this would be emergent. Right. Even with, even though we start from the charge, we can also produce the boson mass from the power interplay between the power and the charge.
Cool. So now we thank the speaker again. During a break, we could really discuss questions you want to ask the speaker. So let's come back to 4 for the final first day. Yeah. Enjoy the coffee and some snacks. Sure.
Very nice slide.
So we
consider the average. Oh, the microphone is worse.
yeah.
Typically,
Yeah.
That's really good. Guarantee that the room. Yeah. Because sometimes if you got the average, it's the average before that, maybe not reason. That's maybe.
电池，来这里，放电池过。好，没有，这边有，这边有，这边有。
Actually, you can see the Gaussian when the right distribution. For some cases, I think I can imagine calculation is very important. Yeah. Oh yeah.